collaborator in the Serre-Green-Naghdi equation, Stefan Popine. Okay. So this particular talk is going to sort of focus on, at least the early part, on shallow geophysical flows. So those are obviously they come from a variety of sort of geophysical events. A tsunami, for example, is considered a shallow flow, or a debris flow down, say, generated by, say, a volcanic activity or underwater, some kind of underwater landslide, can also be modeled as a shallow geophysical flow. The shallow water wave equations are a coupled system of nonlinear PDEs where, and I'll explain a little bit, say a little bit more about the derivation of these, but basically we model a depth averaged height. So they're a set of depth averaged equations in which we assume that the vertical velocity, in which we assume that the horizontal velocities, this is the 1D version, the horizontal velocity has been depth averaged. H is a water column height. G is, we have a gravity term. And then typical in these equations, we include a bathymetry term. So, or some bathymetry or bottom topography. So the sort of the shape of the bottom of the ocean, or sort of, yeah, so here's just a kind of a schematic of the sorts of the various terms involved in this kind of, in this shallow water model. So we have typically a characteristic height field and a characteristic amplitude of the waves. We have a characteristic length scale. So the actual height would be, you know, the depth, sort of the free surface to the bottom of the topography there. And the bottom topography would typically be measured from, say, some sea surface height, say often 0, to the ocean floor. And then our free surface, eta, is then typically height plus the bathymetry. And the parameters that are, so in the fully nonlinear shallow water equations, we assume that the amplitude, the ratio of amplitude to this characteristic height, H0, is order 1, but this shallowness parameter, mu, which is the height divided by this characteristic length scale, is much smaller than 1. So that's kind of the regime in which we're operating here. And then discretely, what we model are sort of the height at these, at discrete locations. This water column height is the thing that we're effectively solving for. So here's an example of shallow water flow in a tank. So the idea here is that we have some initial perturbation to the free surface. We have some underground, in this case, we have flow that runs up onto a shelf that hits a wall. Now this doesn't look particularly shallow, but when you look at the length scale, at the left edge, the height scale here on the left is actually on the order of centimeters, whereas the length scale in the horizontal direction is in the order of meters. So if we were actually to look at the true scale of this problem, this is more what that initial perturbation would look like, and this is what the run up onto this shelf would look like. Okay, so this, I think, is, you know, this is where sort of this shallow regime really kind of makes sense. But often we see these pictures and they really kind of don't look terribly shallow, but at scale they really are. Okay, so this actually is, so we can actually do an experiment where we solve the 1D shallow water equations in this sort of wave tank setup. This was actually an experimental setup. So we actually, for this particular problem, I'll be able to compare my results to some experimental results. And what we see is that the shallow water has this characteristic feature. It develops a shock at the leading edge, and that's because this wave speed actually depends on height. So for example, for water that's fairly deep, we're going to get faster speeds, and we get slower speeds in shallower depths. And so these faster speeds will tend to overtake the lower speeds and develop these shock fronts. So there's a shock, and then behind that shock we'll get a rarefaction wave. And so here, one of the characteristic features of these problems is a jump in the solution. So we have this discontinuity in the solution at that shock front. And so special methods are required to actually solve these problems. So here's how exactly what would happen in this particular case. So we see that we have two shocks, one right going, one left going. The left going one hits the wall, the right going one hits the wall and bounces back. This star here is a gauge where I'm actually going to record the height of the water as it passes that gauge. So it's going to hit the gauge, so nothing happens. It hits the gauge, it hits the wall, reflects back, hits the gauge one more time. So we can actually plot the solution, the height at the gauge as a function of time. Okay, so here's that gauge height as a function of time. And of course, nothing happens for a while. The wave hits it initially, and then it hits it a second time, and then the wave passes the gauge. But we also, for this particular example, we have experimental results as well. So we have, so this was an actual experiment that was done where they actually measured. They had installed gauges in this 25-meter wave tank. The experimental results are actually quite different from the shallow water wave equations. It's clear that we're not capturing the peaks in this solution. So we get, we essentially can correctly get the time at which the waves hit the peak or hit the gauge. But what we're missing is sort of these heights. And of course, this can become important if what you're trying to do is determine how high you should build your seawall to protect, say, from an incoming, some kind of incoming, say, storm surge or waves or something like that, or tsunami. So what we want to try to do is see if we can actually correct the shallow water wave equations to account for what effectively are dispersive effects that are not getting included in the shallow water wave equations. Okay, so again, under the assumption of this fully nonlinear regime in which the ratio of the amplitude to the characteristic height is order 1, but in this very shallow regime where our shallowness parameter is small, we have the classic shallow water wave equations. And then what we're gonna want to develop is and then at least what we're proposing, or I should say, yeah, we'll see. We can actually, it turns out what we can do is actually correct the shallow water equations with a correction term that accounts for these dispersive effects. Now, it's not at all obvious why, why the correction should take this form at all. Why should it even be possible to simply add some term that looks a bit like a source term to the shallow water equations and come up with something that can somehow model these dispersive effects. Well, so that's what we want to, so in the next couple of slides, we can, to some extent, justify why this particular form, which happens to be convenient for computations, would be a reasonable approach to take. Okay, so how do we derive the shallow water equations, and then what we want to solve, which are these Green-Naghdi equations or Serre-Green-Naghdi equations, which actually are this formulation involving these dispersive effects. So, well, the shallow water, we start with incompressible and irrotational flow, so potential flow. In this particular picture, it's a 2D. We actually would solve a 2D Laplacian, and of course, in the fully 3D regime, we would have to solve a 3D Laplacian, where the velocity is the gradient of this potential, and this velocity field is curl-free because, again, it's the gradient of something. So we impose, so the potential satisfies at the lower boundary. We have a no normal flow at the lower boundary. At the upper boundary, we have this condition that fluid particles can't cross the interface. This is effectively a parameterization of the free surface eta. And then we have this equation that actually accounts for the inertial effects, this Bernoulli equation that is another free, so we have two conditions on this free surface. And this, of course, is the classic equation for free surface flow. And from this, we can actually derive the shallow water wave equations. So the idea is to reduce this potential flow equations, which would be, of course, 2D in the example I just showed you, or fully 3D if we were interested in a 2D surface flow. And so we want to reduce it to 2 equations for a surface potential, so that are effectively what would be a full 3D problem actually becomes just a 2D problem for a free surface. So that is in fact what the shallow water wave equations are, okay? So we can expand this potential phi in terms of a shallowness parameter in this, again, in this shallow regime. And so we end up with a phi, sort of this potential that looks like a phi 0 plus mu times phi 1 plus some higher order terms. And we'll call that potential psi. So this potential on this sort of, it's the value of the potential on the free surface takes on this particular form, okay? And it's a little bit funny looking, but it's actually not terribly difficult to derive. I'll give you some references here in a minute. And then we can actually average the gradient of this potential, okay? So we can do a depth average of this gradient to get an average velocity field. And what we end up with is, and if we carry out this out to sort of, you know, at the 0th level, we effectively will get the shallow water wave equations. But if we continue to the higher order, include the first order term in this shallowness parameter, we end up with an extra term, this T of H, where T now is this funny operator that looks like it's actually the gradient of a divergence. Okay, so the divergence, so this funny operator here. So this gradient term comes from there, and this divergence term comes from here. Okay, so then what we end up with is, and again, it's not obvious where these terms come from, so I'll have to, but what we can eventually do is formulate our the 1D Green-Naghdi equations as shallow water wave equations plus a correction term where this D is the result of solving an elliptic-like operator, okay? Now again, the splitting isn't at all obvious from what I just showed you, okay? So in fact, there's a series of papers that actually derive the original formulation, this initial papers by Lons and Bonington, okay? Which actually derive these original asymptotic two-dimensional time equations for surface water wave propagation. And then there's another series of papers by a similar group of by the same group of authors plus others that actually will derive the sort of the splitting that I'm showing here. Okay. So the full set of equations derived from by Lon and Bonington look like this. So we have something that looks like the shallow water wave equation. So this is the mass conservation equation, and then something, and then this formulation here is actually derived from this Bernoulli equation. And here we can see our operator T shows up as this implicit operator. So how we get from this to the formulation I just showed you actually takes some work. So there's a splitting approach that you have to sort of make some arguments as to why we can actually computationally solve it as shallow water plus this correction term. But it comes from this basically. And what I didn't show you in the previous slides are any terms involving a bathymetry. So anytime, so this B is bathymetry. Okay, so that shows up in both the operator itself and in the source term. Okay, so this Q effectively will become a source term to our elliptic-like operator. Okay, so this is actually the formulation we're going to work with. There's several different formulations to these there's several similar formulations to these equations. And I've chosen to work with this one. And it's amenable to computations because it basically is formulated as corrections to standard 2D shallow water wave equations. And the corrections can be treated as a source term handled in a standard way. So we would have to sort of, the downside, of course, is that this particular formulation requires solving a coupled system of elliptic equations. And then it's not so clear that, you know, how do we handle the source term near shocks where the height and the velocity fields are no longer differentiable. Okay, so there's some drawbacks to worry about. Our focus recently has been on simply just solving these elliptic equations. Okay, and we haven't yet started to think in any depth about, you know, what happens near shocks. Okay, so to see what happens in 1D, it turns out in 1D these equations are fairly easy to solve. They simplify considerably. So I implemented a 1D Serre-Green-Naghdi solver using, as for the shallow water wave equations, I use the wave propagation algorithm in ClawPack and GeoClaw. So Randy Levesque, Marcia Berger, Kyle Manley, David George, and others have all been involved in developing this GeoClaw solver and associated Riemann solvers. The elliptic-like solve is formulated as a tridiagonal system. And in 1D, we simply can solve that with just using a LAPACK tridiagonal system solver. So that turns out to be easy. And then we simply, at least as a first step in solving these equations, we are just going to alternate steps of a hyperbolic solve followed by a solve for these correction terms. So a hyperbolic solve followed by an elliptic solve, followed by a hyperbolic solve, followed by an elliptic solve, where the elliptic solve is, you know, we solve for these correction terms that then get added as source terms to the shallow water wave equations. So as an example, we can look at sort of a 1D tsunami. The idea is that we have a domain length of L, a wave height that's clearly much smaller than the domain length. So 0.1 over L gives us a shallowness parameter that's much smaller than 1. The depth h is approximately 1. There's no bathymetry in this particular problem, and we'll solve this out to time t equals 2000. And this is an example that was taken from a paper by Stefan Popinet, who developed a similar solver using his adaptive code, Basilisk. And I'll show you results from his code compared with our code. Okay, so then if we go ahead and solve this, and I've solved this using 4 different codes. So we have first just the shallow water wave equations, so we can see the difference between kind of the shallow water equations without any dispersive terms and the shallow water equations with dispersive terms. Okay, so there's just the shallow water wave equations themselves. There's my implementation, which uses the GeoClaw solvers with the dispersive corrections that I just discussed. Then there's another code called BoostClaw, which was developed by Jiwon Kim, a student of Randy Levesque's, who developed this code as part of his PhD thesis at the University of Washington. And then finally, there's this Basilisk solver developed by Stefan Popinet in Paris, who, so I've got these 3 codes that I can compare, plus the code to the shallow water equations. Okay, so then after we let this thing go, and after a while, it's pretty clear that the shallow water equations have no dispersive effects, whereas the other 3 solvers all have some version of dispersion, and the agreement is actually surprisingly good, especially considering the BoostClaw. So the GeoClaw solver, my GeoClaw solver, and Basilisk are using essentially the same solver. So we're both using this solver that I just described. BoostClaw uses a slightly different version. It's a solver developed by a different group, but with the aim of you know, including these dispersive effects. So its results are slightly different than ours. So we let this thing go. So here we're at time 90. And then time 700. And still we see really good agreement. I was really happy to see that all 3 solvers are effectively producing the same thing. which, you know, kind of gives you some confidence that these wiggles are not just some kind of, you know, weird numerical artifact. And then only at the very last time step is there some deviation which we haven't completely explained between the basilisk code and the other two codes. Okay, but it's clear that what's really impressive here is that using just the shallow water equations themselves would you know, significantly underestimate the height of an incoming wave. Okay, so again, in a system where you're concerned often as much about the height of the incoming waves as arrival times, you know, these dispersive effects are going to become important. Okay, so this is the 1D solver. Now, and let's just see exactly whether we can actually reconstruct the initial, you know, can we somehow resolve this difference between the experimental results and our numerical results. So now if we let this thing go again, so we'll start to see the dispersive effects after that hits the wall. So again, that, you know, we're going to record the height at the gauge. Okay, so here's the solution so this is now what we see is that we're actually getting something close to the heights that we missed initially. So this is our computed solution versus the experimental results. And so I think this is a pretty good evidence for the need for these dispersive effects in many scenarios. The challenge, of course, is actually getting these in 2D. In 1D, we could use just an elliptic solver and life was good, or a tridiagonal solver, and that was easy. The challenge now is how do we incorporate this into our code? So there's several different codes. There's that are doing adaptive mesh refinement. I happen to have a code that does adaptive mesh refinement. So we have this shallow water equation solver using finite volume methods on adaptively refined meshes. And I'll say something about the particular code that I use in a minute here. And what we want to do is implement this Serre-Green-Naghdi solver. But what we need is some kind of variable coefficient elliptic solver on an adaptive mesh. Okay, so we're working on two approaches to constructing this implicit solver. When what I'll talk about today is this iterative solver based on a multi-grid preconditioned BiCG stab solver, and that's developed by Scott Ayton at BSU. And I have another student working on a direct method based on a hierarchical Poincaré-Steklov method developed by Adriana Gilman and Martinson back in 2014. And Damon Chipman at BSU is a PhD student of mine working on that project. Scott's project is much farther along because he's been working with us for several years, and Damon just started, so we're getting off to a good start, but we're not quite at the point where we can solve the Serre-Green-Naghdi equations with that code. So the challenge, of course, is that the mesh changes every time step, and it's not obvious how to amortize any setup costs associated with elliptic solvers. So this is just the shallow water wave equations in a box. So a bump showing sort of basically the adaptive features. And I'll say a bit more about the code that I use to solve this. So I've been involved recently in this forest claw project, which is a code I've developed with Karsten Borsted at the University of Bonn in Germany. So it's a quadtree code. It's an adaptive mesh code that relies on quadtree refinement. Okay, and each leaf of the quadtree is actually a Cartesian grid. So we have multi-rate time stepping. It has multi-block capabilities. So we can do, for example, the cube sphere. And we have sort of set it up so that, you know, with the idea that it can be extended by several solvers. So for example, the ClawPack, we've extended it with the ClawPack solver, with GeoClaw, and several other solvers. But it's essentially the numerical, it's essentially that the time stepping and the numerical algorithm for the adaptive mesh refinement is based on the Berger-Oliger-Colella approach to AMR. So this is kind of the idea. The idea is that we have these leaves in a quad tree, and each leaf is occupied by a fixed size grid. and the grids will communicate through copying and interpolation and averaging, but in these ghost cell regions, okay? You know, there's sort of lots of different customization actions. I like to think I have lots of support for legacy codes, so that if somebody had a single grid solver, there would be a way for them to incorporate their single grid solver into this forest claw project. And we've been pretty successful in doing that with several codes. So as I mentioned, there's several extensions to the code. I've kept it written in C so that it's, you know, reasonably easy code to access for maybe people not up to speed with the latest C++ 17 standards. And currently we've been focusing mostly on solvers for finite volume meshes, although somebody who has, say, a node-based mesh could come in and write their own patch and include it. So now we want to solve an elliptic problem on this, on these adaptive meshes. And of course, you know, it turns out that you know, in some sense, it's easy to think, well, solving an elliptic problem on a Cartesian mesh, you know, isn't that a solved problem? Yeah, well, turns out not really, especially if you have your own kind of quadtree mesh and you need to solve an elliptic problem on it. And so we had several goals. We wanted to avoid forming a matrix if at all possible, okay? So matrix assembly, it's not that, you know, certainly if you're in a finite element world, you think nothing of matrix assembly. You know, if you haven't assembled 10 matrices before breakfast, you know, you don't deserve to be called a finite element person, right? But in the quadtree meshes, the way that we've set them up with these sort of finite grids, with these fixed patches in each leaf, you know, you have to do something special at grid boundaries, right? You have to interpolate, you have to average, and incorporating all of those details into a matrix would be challenging, to say the least. I don't want to say it's impossible, and it has been done. People have done it, okay? But it's not something that we particularly wanted to do. So this makes things like PET-C less attractive, because PET-C, of course, wants a matrix. You pass it a matrix, and at least in its standard formulations, and then it will be happy to use any number of the solvers available in PET-C. But what we really wanted to do is take advantage of local patch solvers. So we wanted to be able to use the fact that we do have a lot of structure in our adaptive mesh refinement. So is there a way to glue together solvers on local patches? Another challenge is that the mesh is modified at each time step, so methods with expensive setup costs were not going to be good options. And then there's really just not a lot available if you're kind of trying to work in this space, right? So you're sort of semi-structured, and so of course there's obviously lots of solvers for uniform Cartesian patches. Hyper has some support for a semi-structured mesh if you know, and it allows you to sort of facilitate matrix assembly so that you could then pass your solver off to one of Hyper's solvers, say the Boomer AMG. But, and we started to go down that path, but really realized at some point that we were going to have to write our own solver. And so that's what Scott Ayton has been busy with for the last several years, working with us on this code that ThunderEgg, which is now to the point where I think we can call it a general elliptic solver. It's a 2D, 3D general elliptic solver package, and it's based on multi-grid preconditioned BiCG stab. It works on the adaptively refined quadtree meshes that are generated by forest claw. Our focus has been on second order finite volume discretizations of the elliptic operator, although certainly users can define their own general operators on Cartesian patches. We haven't tried anything other than yet the second order finite volume discretizations, but there is definitely a path to other kinds of operators. It's conservative in the sense that we don't generate any artificial source terms that correspond boundaries. One of the most recent additions is because what we needed for the Serre-Green-Naghdi equations was the ability to solve coupled systems of elliptic equations. So we've just added that. It can use fast solvers when appropriate. So for example, if you happen to be solving, say, a Laplacian, just a Laplace's equation, and your patch, and you don't have any variable coefficient, let's say, you can use an FFT solver on your patch solvers. There's also a Sure complement solver available, and this is somehow again, just for the constant coefficient problem. It's parallelized, so we can run it in parallel. And Scott's done a really good job of providing online documentation and also, really making it a real sort of software package with continuous integration. It's based on CMake. So he's put a lot of work into that. And it's available on GitHub. So Scott's here in the audience, I think. So Scott, I'm letting everybody know that your code's available. And I encourage people to try it out because I think it's actually at a point now where it's really, it's really nicely done code. Okay, so how far are we in actually getting the Serre-Green-Naghdi solver going? Well, so we've put a lot of work into developing a variable coefficient Poisson solver. So that's kind of where we're at now. And we're really close to getting the time stepping. I've been working recently on incorporating the time stepping, incorporating this elliptic solver into a time stepping scheme so that we can do the full Serre-Green-Naghdi equations. But essentially all of the components that are needed, including this ability to solve coupled systems, is available in this ThunderEgg software. But what I'm going to show you today are just some results for this Poisson problem. So we actually chose a problem very similar to this. This is one of the problems that we've solved. So this is a solution to a Poisson problem, okay? And so here, for example, how do we do the refinement in that case? Well, about all you have to refine on is the right-hand side. And basically, so effectively for this particular problem, what we're refining on is the curvature. So it's the Laplacian of our solution, effectively. So we knew, of course, we knew ahead of time what the solution was. So when we compute the Laplacian of our solution, we can then use that as our right-hand side and then base the refinement on that. And so what you see here is that, the solution has positive curvature in these yellow regions and negative, or the right-hand side, excuse me. The solution has what we can think of as curvature. It's the Laplacian, right? So in these yellow regions and negative curvature in these blue regions. And so that's where we chose to place the refinement. And that's what the solution looks like. So the solution is, of course, refined in the places that we would like it to be refined. So we did several, so we've sort of worked hard to make sure we can, justify that the accuracy is what it needs to be on a slightly simpler problem. And so one of the tricks in developing these solvers for adaptive meshes is that you really spend a lot of time just coming up with diagnostics. So for example, computing the error no longer is a trivial exercise. So a fair amount of work goes into that, but we've got all those tools sort of built into Forest Claw now. So we can do things like compute the error and look at various convergence of rates. And of course we have a second order scheme. So we're expecting, sort of textbook second order, which we see eventually. Now for this problem, of course, if the grid is too coarse, we're simply not resolving the solution at all because this had a fairly sharp interface between at the, sort of the boundary of this star shape. But once we get up to sort of finer grids, we see kind of the textbook second order accuracy. We've done some, so this is just comparing it to several other adaptive, several other elliptic solvers out there, okay? And so at the bottom here, what I have is effective resolution, meaning that the resolution, sort of the resolution for the adaptive case, the resolution at the finest level. So I've got 5 different codes that we looked at. So uniform would be a grid that uses the ThunderEgg solver, but that refines everything uniformly. So that essentially everything is at the same level of refinement. So it's no longer, so it's still a quadtree mesh, but it's a sort of every, there's the bottom, there's a, yeah, it's there's sort of no missing leaves. Then there's the adaptive version, which I showed you pictures of. There's a what we call single. So single in this case would be, instead of solving on a quadtree mesh with multiple leaves, what if all we do is just simply don't allow any refinement, but just increase the resolution of a single grid. So these first 3 solvers are the ThunderEgg solver I just talked about. This red one here is MATLAB's LU solver, and I believe it was using UMFPAC. I think UMFPAC is now incorporated into the MATLAB solver, but it's basically MATLAB's sparse matrix solver. And then, of course, we compared it to FishPack, which was one of the first packages that I got to know, I think, when I was taking PDEs from Chris Bretherton. In fact, I implemented the FishPack solver for a course and have ever since had a fondness for the FishPack solver. And so what we see here is actually that the nice thing is that the difference between the uniform and the adaptive solver for ThunderEgg, this blue and this orange, are effectively the same. So we basically take no cost hit for solving on an adaptive mesh versus solving on this uniformly refined mesh. It also shows you that just solving using just BiCG stab on a single grid is you're just going to lose performance. You just spend, your grid gets way too big to fit in memory, and so there's all kinds of issues that can arise on trying to solve on a single big grid. The MATLAB solver is slightly faster, but of course here as we get closer to the larger and larger grids, it's not so clear anymore. But MATLAB again is using just a big single grid. It knows nothing about adaptive meshes. It doesn't know how to, so of course it's not something we could even make use of, even if we wanted to, and it's only slightly faster. And then of course, the FishPack code, which is based on cyclic reduction, is going to be a winner, but again, it's on just a single uniform grid. So it's not something we could of course incorporate it as a patch solver, and that might be something we might think about doing. But yeah, that of course it's going to be really hard to beat that one. So we were quite happy and then the other thing of course is that as we increase the resolution, the degrees of freedom per second, which is what I'm showing here, is effectively constant. Okay. We've done some preliminary parallel scaling results. We've just now we have access to a new big machine at Idaho National Labs, which I think just this week we can now get access to it. So we're going to start running on that. But at least on a desktop, which is where often a lot of these codes are run, the 2D shallow water codes in GeoClaw, for example, can all be comfortably run on a desktop. So it's not even really necessary to use supercomputers for some of those problems. But we're getting, what we see here is that these blue is just a single, one core. The yellow is 2 cores, and the green is 4 cores. And the speed up, of course, we expect a speed up of 4 on 4 cores, a speed up of 2 on 2 cores, and on 1 core, of course, we don't expect speed up. And so what you see is that as we get to large, as the effective resolution increases, we of course have more patches. And so we're able to take more and more advantage. And so we have less communication overhead per patch, right? So we see, closer to our sort of theoretical speed up of 4. But in fact, even at sort of moderate resolutions, we're getting really close to factor 4 speed up, which is really good. And then the same thing is, factor 2 speed up on 2 patches. So, I think this is actually really promising. We want to, of course, test it on much higher core counts, but we'll do that in that's kind of one of our next projects. And then so that's pretty much where we're at. So the ThunderEgg solver it's a standalone solver with its full set of examples and everything, but we've now incorporated it into Forest Claw, so it can be called directly from Forest Claw. Our current focus is on incorporating the solver into a time stepping loop. So, and there's no major technical challenges there. It's just, debugging time basically. And then we have to implement this 2D Green-Naghdi solver, but the way that ThunderEgg it's now been formulated to a point where it really is just a matter of coding up the operator. We've got support for systems of elliptic equations, and the user can define their own variable coefficient equation with whatever variable they want to use. So then ultimately what we'd like to do is include these dispersive corrections in the GeoClaw extension of Forest Claw. So Forest Claw is this, again, the quadtree code that I've been working on. And GeoClaw has been incorporated into Forest Claw. So GeoClaw is, of course, the code that Randy Levesque, and he may talk about that later this afternoon. So we have a version of that in Forest Claw, which would allows people to basically run GeoClaw in parallel on a sort of on a distributed parallel environment. And then a sort of parallel to all this work is this development of the HPS solver, which is a direct solver as opposed to an iterative solver that Damon Chipman is working on. So I want to thank you again, and I think that wraps it up. And I'm happy to I'm happy to take any questions.
Okay, any questions?